Hello and welcome to Graphing from Gradients, the video in which I show you what to do when the examiner throws a graph at you that shows you the gradient, which I'll be drawing on this axis here, and asks you to draw the actual graph down below. One thing I should add is that even if you have a graph of the gradient, something like this, saying the graph has a gradient of 1, that is not enough information to actually draw the graph below. A lot of people would jump to conclusions and say, okay, it's a straight line with the gradient of 1, so it must look something like, I'll start it here, something like this. But that would be making the assumption that the graph starts at 0, 0. It could just as easily start down below at 0, negative 1 and run up parallel. So just recognize that derivative graphs describe a family of graphs down below, not necessarily one particular graph, unless you have that key bit of information. Okay. Whoops, I need that part. So let's mock up a very simple derivative. We won't have 1 there, we'll make this a half. We'll run a line across and we'll say down below y equals negative 1 where x equals 0. So that gives us the coordinate 0, negative 1. So go down to the graph below and mark in the point 0, negative 1. 0, negative 1. And what I'm going to do is put open circles at the end of this graph here. We'll leave this as narrow, and we'll see how that affects the graph down below. So 0, negative 1, let's say it's a closed circle there. It has to have a gradient of positive a half throughout its entire run. So for every 1 that it goes across, it must go up a half. So let's try that. Go across 1 to x equals 1, and it must go up a half. So we get the point 1, negative 1 half. Go across another 1 and we have to go up another half, so we get 2, 0. 2, 0. And the graph will keep doing that, going across 1, going up a half, going across 1, going up 1 half, all the way on to infinity. So instead of completing that step a number of times, we can simply say, okay, it's a graph with a gradient of a half, it's a straight line, and it looks like that there. Now let's talk about why the derivative has an open circle up here. Well, even though I've said the graph down below has a closed circle, and look, it could be an open circle, but we'll just say it's a closed circle here. If the graph has a closed circle, which means an endpoint, you can only take the derivative from one side here, and if you can't take the derivative from both sides, then the derivative does not exist. So the derivative technically doesn't exist at this point. That's why it's an open circle. But if we look at a point, say here on the graph, where we can take the derivative from both sides, which means the gradient between this point here, 2, 0, and the next point along this way, and the gradient between 0, 2, 0, and the next point along this way is going to be the same. But again, down here, we can only do it in one direction. There is no derivative over here. That's why the derivative exists for all these points, but not for this point over here. So let's look at a more complicated function, a derivative function, one that is known as a hybrid function. So just think it's going to jump around a little bit. Rub all this out, put a line through there. Okay, let's draw a function that starts off at 0, negative 1 goes along for 2 and terminates at 2, -1, then jumps up to 2, 0, runs along for 1, terminates at 3, 0, and then jumps up again to 3, 1, and runs along to 4, 1, and then moves down gradually, I'll get a ruler out here, to terminate at 5, 0. So I'm actually going to close that circle there. So this circle it's no longer an endpoint. We can say it's just another part of the graph. Mark it with a cross, and has endpoint here at 5, 0. So this is a very common question for graphing exams. They say, here's the derivative function, and can you please draw the graph down below? Now, as I said before, any derivative only describes a family of graphs. So graphs that all run, well, sort of parallel to each other, but exist at different heights. So this is an example of a family of graphs. What we want is the one particular graph to draw. So we need a bit of information. I'll say the graph below, by which I mean the lowest one down here, passes through, let's give the coordinate 0, 1. Okay, so we go down here, and the first thing we do is mark in the point 0, 1. Now, between 0, 1 and 2, I'll make that line straighter, the graph has a gradient of -1, given by that value there. So for every 1 that we go across, we have to go down by 1 as well. So we started up here, we'll put a closed circle there. We know it's a closed circle because the graph does in fact pass through that point, and we have to go across 1 and down 1. There we go. And then I keep doing that until I get down here. So if I've gone across 2, I must have gone down 2, so I'm now at point 2, -1, because -1 is 1 take away 2. Now between 2 and 3, the graph has a gradient of 0, which means it just cruises along like that, it's flat. And between 3 and 4, it has a gradient of -1. So if I'm going along, sorry, it has a gradient of +1. If I'm going along 1 here, I have to also go up 1. So I reach 0. I'm marking that point there, that's 3, -1. And then I'm going along 1 and up 1. So I get to 4, 0. Now the final part of this graph is the trickiest part. Have a look at this. You start off with a gradient of 1, but the gradient drops as you go along until it reaches 0. So we're actually going to have a flat graph at the end. It's going to start off with the same gradient and then flatten out like that. Knowing how high this graph gets can be solved by calculus or by a bit of geometry. So we'll do the geometry method. First of all, let's say if the gradient stayed at -1 up there, then this graph would continue up and finish over here at 5, 1. But it's not going to do that because the gradient actually gets less. So it's going to look something like this. So we want to know what this coordinate over here is. The way we work that out is to say, okay, the height gained by the graph between here and the endpoint here is the same as the area under this last triangle. And the area under this last triangle, it's very easy to find. We say area equals half base times height, which is equal to half base of this triangle is 1, and the height of this triangle is also 1. So all up it equals 1/2. So this graph down here must have gained 1/2, and since it's from 0, it will actually come up to the point 5 1/2. There we go. And that last bit is actually a quadratic, and you can work that out using a bit of calculus. I hope that's helped you understand how to draw a graph from the gradient function. The key things to remember are you do need this bit of information. The area under the derivative function shows the increase in the graph down below. So this over here is a negative area of 2. So this graph over here between 0 and 2 has actually gone down by 2. And the final thing to remember is that even when the derivative function is undefined and jumping around, the graph won't jump around like that. The graph tends to connect to itself. I just had a thought on this function here. Each line here corresponds to a series of curves. This line here corresponds to just one because we know the point. But the next line along here, the gradient of 0, this graph here, if I had said it's continuous, I didn't say it was continuous, I've just assumed that. If this graph here didn't need to be continuous, it could look like this. The first line would have to be the same. The second line could be anywhere. It could be up here, could be up here, it could be down below. The third line again could be anywhere. And the fourth line could be anywhere again. So just make sure you know that the graph below is continuous, because that'll let you be sure when you sketch it that it all connects up. I hope that helped. That is graphing from gradients.